of these presentations are to present the statistical framework behind AstroGeoFit. So what's the reasoning behind it, why we expect it to work. And hopefully I will give you some ideas of like not only AstroGeoFit, but how you can apply some advanced statistical methodologies to other problems. So you know that AstroGeoFit is trying to solve basically two slightly different problems. So from stratigraphic data, so from a proxy, you want to retrieve a time-depth relationship. You want to see where you want to correlate your proxy to where the Earth was in the past, which you propagated with a numerical simulation, so that you can match the astronomical solution you generated with the proxy. And also, you might want to constrain the astronomical signal itself, thanks to the data, beyond a certain horizon, where the chaos prevents you from knowing exactly where the Earth was in the past. So in practice, this you know better than I do, but you have a proxy. So for example, here this is a grayscale. You have here this is you have your astronomical solution where you pick exactly which components you want, and you match the values and peaks of your proxy with the values and peaks of your astronomical solution. That's how we do things so far. So here, in that case, the astronomical solution is precession minus 0.5 obliquity. But here, when you do things by eye, then you have potential human biases. When there is some missing data, when the sedimentation rate is very slow, maybe you will miss a valley, you will miss a peak. So this will create a lag in your solution. And also, you need to select an astronomical solution. Here we selected precession minus 0.5 obliquity, but it's not necessarily exactly what is going to match the patterns that you see on your proxy. So you're not necessarily sure how to select the reference astronomical solution. You don't necessarily know how to quantify the uncertainties on your time-depth relationship. So you might have some correlated noise in your data, so it means that at a given depth, the value of the noise depends on the values of the noise at the previous depths. So it creates some sort of low frequency signal, and it's not clear how you factor it in your analysis. You don't know if you have an uncertainty on the astronomical frequencies, so how does it propagate to the uncertainty on the time-depth relationship? Maybe there are gaps in your data that you don't know how, and it's not clear how to identify them. So these are some limitations that we're trying to solve with AstroGeoFit. Okay. And so to present this framework, we will go step by step. First, today I will present the AstroGeoFit model and how to fit it simply to the data with a sort of naive approach. Then we will see how to estimate the uncertainties on the parameters of the model, so uncertainties on the astronomical parameters, uncertainties on the time-depth relationship. Then we will see that in AstroGeoFit there is a parameter which selects the complexity of the model and which needs a particular care. And this will be the object of the third lecture. Fourth lecture, we will talk about computational aspects. So basically, this is what we want to do, and this is how we do it in practice, like several tricks that we use to make the computations efficient. And the fifth lecture, I will present everything again, but from the perspective of someone who is trained in statistics. So this is where I hope that you will find some ideas that you can apply to your problem. So let's dive in the AstroGeoFit model. Here, basically the aim of this lecture is to build a model of the form where your data that depends on the depth, the proxy, is a model of depth and some model parameters, and these model parameters represent what you want to know. So when you fit your model to the data, you will estimate these model parameters, which will give you information on the time depth function, on the astronomical signal, and on the noise. So some mathematical notations. When I will use bold font, it means that it's a vector. So for example, if I have several fundamental astronomical frequencies, I will denote them by a bold font omega, which is a vector or a tuplet of the frequencies. This is the data, the proxy you want to model. So this is the actual data. This is the astronomical signal. So here you see that it might depend on d or the depth, or t the time in the past. And t of d and of the parameters is the transfer function, which gives you the time as a function of depth. And these are the parameters that we will try to tune to estimate the transfer function. So, back to our objective, we want a model of this in this form. So the signal plus the noise. Here, the signal, you can make it depend on t, but t depends on the depth through the transfer function. And you have some noise also, some value of the noise which perturbs your measurement. So you see that the noise are basically the wiggles that you have, which might depend on unknown geological processes. Okay, so in our parameters, we want to include parameters of the astronomical signal, the frequencies, the phase, the amplitude, the parameters of the time depth transfer function, and some parameters of the noise that characterize the typical amplitude of the noise, its typical time length, and so on. So now we will include these parameters in our definition. The signal, so the parameters of the time depth transfer function, they are in the time depth transfer function. The parameters of the astronomical signal, they parameterize the signal you're trying to retrieve. And the parameters of the noise, they are parameters of this additional uncertainty you have on your data. So we will go step by step and try to understand these different terms in the equation, the astronomical forcing, the transfer function, and the noise. And let's start with the astronomical forcing. So we've just had a lecture by Jacques on this forcing. It's been known for a very long time that the astronomical quantities such as eccentricity, obliquity, and so on, they are very well modeled as a sum of periodic signals, so a quasi-periodic signal. So you know that you might represent it in this form. So here, the astronomical forcing might represent, yes?
Yes, what do you call the parameters actually? What is in the parameters?
This is, we will get to it.
Okay.
We will get to it. What I mean is that we want information about the astronomical signal, about the transfer function, and about the noise. And this will come in the form of a parameterized function. And now what we will do is to dive in the exact form, the exact parametric form of all these terms, but one by one. Okay. Because otherwise the equations will take too much space. So yes, so you want a quasi-periodic model. So another way to represent this quasi-periodic signal is you have a sum of sinusoidal signals which have different frequencies, different amplitudes, and different phases. So what does it mean? It means that the amplitude of the geological response is a free parameter. So whether your signal is going to be like this or like this at a given frequency, this is something that you will fit on the data, that you will decide based on the data. Also, phase is a free parameter. It's not fixed, which means that it very well encompasses the case where you have a delay in the response of the proxy to the astronomical forcing. So for example, here, suppose this is the one frequency of the astronomical forcing. It's completely included in the model that this particular frequency has a response which has a different amplitude anyway, it doesn't make sense to speak about the amplitude of the astronomical forcing and in the proxy because these are different units, so you need a conversion factor anyway. But you might also have a delay in the response of the geological response. So another important thing to note is that on your data set, you assume that the frequencies, the amplitude and the phase of a particular frequency of the astronomical signal stay the same. So we've seen before that the frequency evolves over time, but here, at least in this version of AstroGeoFit, this might evolve in the future, but in this version, we assume that the frequency is going to stay the same. So you don't want to apply AstroGeoFit to data over 70 million years, for example. Okay. What it means also is that you don't have nonlinear responses. So if this is the astronomical forcing, you can't model at this frequency, and you expect this frequency to be in your data, you will need to include other frequencies than your data if you wanted to model the fact that, for example, you have a response which takes the absolute value of your input signal. So you don't, here the astronomical model does not take into account nonlinear effects, or alternatively, you would model this signal by a combination of several frequencies. So just a little bit of trigonometric equations. Instead of writing it like this, so amplitude and phase, I just use the formula for the sine of the sum of angles. So now I have a cosine term, cosine of the frequency, and sine of the frequency, and these two, I will use them as free parameters. So in the end, instead of having k amplitudes, if I have k frequencies, I have two k coefficients. For each frequency, I have one coefficient for the sine and one coefficient for the cosine. And also, instead of using as parameters the frequencies that I see in the data, I will use a vector of fundamental frequencies. And this is exactly what Jacques was talking about. The relevant dynamical variable is the eccentricity times the exponential of I times the argument of periastron. So when you take the modulus of this variable, what appears is the difference of fundamental frequencies. So here they are noted pi in Jacques' paper. In AstroGeoFit, they are the omega parameters. So the astronomical forcing, to summarize, it is a linear combination of the fundamental frequencies of the problem of periodic signals, and these frequencies are parameterized by the fundamental frequencies. So they could be, for instance, the new here, the frequencies that are the frequencies of the oscillations. They could be the difference, for example, of the fundamental frequencies. So we have two parameters, phase and amplitudes, and frequencies. Back to our initial problem. This, as a function of time, now we know what this is. And we want to model the time depth transfer function. This time depth transfer function, we make one assumption, which is that time is a non-decreasing function of depth. So if you take the derivative of time as a function of depth, which is the inverse sedimentation rate, it has to be positive. So it means that as you go further in depth, you go back in time. This is the assumption. This can be relaxed maybe at some point, but in the current version of AstroGeoFit, this is the assumption. And this is where it gets a little bit more hairy. This is the parametrization of the time depth function. So we use knots. So you take an array of depth. These are knots. The value of the inverse sedimentation rate on these knots will be in between bounds, certain bounds. You interpolate, so you choose the value of the parameters of your time depth transfer function in these knots. You interpolate between them, and then you integrate the inverse sedimentation rate to get the time depth function. Okay. For instance, suppose I have two knots. So my depth on 1 meter is, I have one knot at 0 and one knot at 1 meter, and this is my parameter. Now I can have 3 knots, and these are all my parameters, the things that I want to tune in the algorithm to match to match the data. I can have 4 knots or more. And the more knots I have, the more flexibility I have to parameterize this inverse sedimentation rate. So to build this transfer function, if I have data continuously from 0 to 1 meter. So I need to know what is the value of the time at a depth which is given here. So I interpolate between the points that I have chosen. And again, the values here, they are my parameters. So it allows me to tune this inverse sedimentation rate. Here I can vary the value of my parameters, so it will vary the time depth function. And the third step is to integrate. So this is the derivative of time as a function of depth. So if we want to go back to time, we need to integrate this function. So we take the area under the curve, and so on. So, for example, on this particular example, as you take the area under the curve as a function of depth, you will build this function of time as a function of depth. And if I change my parameters, this will change slightly the shape of the time as a function of depth. Okay, so we choose the number of knots. We parameterize the value of where where the knots are as a function of depth. This is fixed, but their amplitude is a free parameter. So, for instance, here with 1, 2, 3, 4, 5, 6 knots, this is one sedimentation rate that I can reproduce. Or this, or this, or this. So the sedimentation rate can also be a periodic function. So you can make the sedimentation rate vary with the astronomical forcing. So this is how you build your inverse sedimentation rate, and to, in the end, get to the time depth function that you will put back in your model, we do an integration with a numerical Riemann integration. Back to our model. The third part of the model is the noise. So now we know what the astronomical forcing is as a function of time. We know how to convert depth to time, and we want to determine what this noise is. So in AstroGeoFit, the assumption is that the noise is an autoregressive process of order 2. What does it mean? It means that the value of the noise at a given depth is a linear combination of the value of the noise at the two preceding depths on your grid. So you have a grid of depth in your data, plus some Gaussian noise. So basically, you would, if you wanted to generate something like this, you would first generate a random noise, then take the linear combination of the previous values of the noise, add another realization of your random noise, and so on. Okay, let's do it step by step. So you generate those from a random Gaussian noise with the variance phi 0. Yes?
What does justify this choice of an autoregressive process of order 2? Why not 3, 4, 5?
Well, I think for the moment there is no clear justification. It's common in the geological literature to have a. I mean, I didn't read much of it, but in what I read, autoregressive model of order 1 or 2 are quite common. But this is something that can evolve. I mean, and this is a good opportunity here. If you have good reasons to believe that, in fact, you need another type of model of correlated noise, this is something we can discuss. And I think Arsène already has implemented some more elaborate models of noise. Yes.
I think in the AstroGeoFit tool, we can implement the other orders of noise, but just for the current version, there's no option to input the order of noise.
But it's going to be more flexible in the future.
Yes. So inside the code, we can change the order. It's just that now it's not possible. For the current version, it's not possible for the user to change.
So you generate the two first value of the noise at your first depth with a random Gaussian noise. Then this is a linear combination of those two values plus some noise, some additional noise that you generated on top of it. Then this is a linear combination of those two plus another value of the noise, and so on. So this will allow you, this is a process to generate, this is a blueprint of how to generate an autoregressive process of order 2. So in principle, you could have autoregressive processes of higher orders. And this is an example of what it would look like. So if you have order 0, so it means that each value of the noise is a new generation of a random Gaussian variable. Then you see it's white noise. You have no particular pattern. Order 2, you start to see that you have some remembrance of what the previous values of the noise were. And if you go to order 20, now you see that the noise remembers at large scales what the value of the noise was. So it makes the noise vary with a lower frequency. And you see that, for example, you could model a stock market prices with autoregressive processes. It's like something that varies, but the value of the price depends on the value of the price the day before. And in the case of order 20, it's the value of the price depends not only on the day before, but 2 weeks before. Almost 3 weeks before. Okay. So this is a blueprint to generate stuff. So I can give this to my ARMA model on my computer and press, each time I press a button, I have something like this. So I generate stuff that looks like this. So you see that you can't try to fit the exact realization of the process on your data. It's like you would try billions of times until you have something that looks like what you have on your data plus the astronomical signal is just not realistic. So what the parameters are phi1, phi2, and phi0, which is the variance of this noise innovation. So in this particular example, I used these values of the parameters. Yes. So one way to characterize the noise is to compute the autocorrelation of it. So here you just take two values which are separated by a certain numbers of lags. You take the product and you average the value of this product. So you see that on these realizations, these exact four realizations, I can compute 4 different autocorrelations. And they kind of look the same. So it's high at the beginning, then it decreases, and you see that the decrease is kind of the same everywhere. And this is not a coincidence. It's because you have a theoretical autocorrelation. So if you were to take the autocorrelation of generated signals and stack them on top of the other, average them, as you average functions like this, they will converge towards the yellow curve. And if you want to understand really what's in AstroGeoFit, a really important thing to understand is that it's completely equivalent. If this is a Gaussian innovation, so if it was a Laplacian innovation, it would be another story, but it's completely equivalent to characterize your autoregressive process with these parameters or with this autocovariance function. So autocovariance is the autocorrelation times the variance of the Gaussian innovation. So when you say this, you say this. You have the same information in both, and this will be important later. So this was our initial aim, to construct a model of the data that depends on what you want to know and that you can fit onto your proxy. So we know that this signal as a function of time is a linear combination of periodic signals with a certain amplitude, a certain frequency, a certain phase. The time depth function is parameterized by n knots, and the noise component is a correlated noise assumed to be an autoregressive process, which are parameterized by the phi, how the value of the noise depends on the previous values of the noise. So looping back to your question, these are the equations, the precise mathematical definitions which define the parameters we are looking for. Okay. Now, this is what we want to fit to the data. So the blueprint of the fitting process is that you are trying to find, first you will try to find parameters which makes this signal kind of close to the data. Then, from there, you estimate the uncertainties on the parameters. This is what we will see on day 2. And remember that there is a certain number of knots in my parametrization of the time depth function, which define the granularity of this function, like how much freedom I have in defining this quantity. And the selection of the number of knots, I need a full conceptual framework to do it, and we will see it on day 3. So, today I will only talk about this particular step. So, you might know the chi-squared, so the difference between your model and the data squared at each depth. This is something that you might be familiar with. Every time you want to fit something, basically you have your model minus the data, you square it, and you try to minimize it. You try to minimize the distance between your model and the data. Yes? Okay. So this is, I rewrote it like this without the parameters to make very clear that it's basically the difference between your model and the data squared. So each time you have a difference, a big difference between, at a certain depth, at a certain point, you have a big difference between the signal and the data. This is something that penalizes your fit. So you will want to bring your model as close to the data as possible to minimize the distance between the two. And the mathematical notation to say that we want the parameters that minimize this function is argmin, for argument that minimizes. So the minimum of the function is the value of the function at the minimum. The argument of the minimum is at which parameters do I find the minimum of this function. So this is all very good. So it would be very good if I had a model only like this. But my model also includes the noise. And in this picture, I don't know how the parameters of the noise fit in. Right? Because, again, here in my definition of the chi-squared, you see that only the time depth function parameters, the frequencies and the amplitudes and phases appear. The noise does not appear at all. So, what do we do? Another super important notion, and if there is one takeaway of the idea how to approach a data analysis problem like a statistician, the first thing you ask when you have a new data analysis problem is, what is the likelihood? And the likelihood is the probability of the data knowing the model parameters. You remember that here, when I say I have a noise epsilon, here this is a random variable. This is something where I can generate various realizations of this random variable. So when I'm writing this, in fact, what I'm writing is a probability distribution. It is a way, a recipe to generate fake data knowing the model parameters. So knowing the model parameters, I can generate stuff. I have a probability distribution. This is a definition of it tells me how to generate fake data knowing the model parameters. And the precise mathematical description of this likelihood in the case of AstroGeoFit is this one. It is simply a multivariate Gaussian distribution. And why did I insist so much on the autocovariance of the process before? It's because this is what defines this covariance matrix here. So the covariance, so the empirical autocovariance, you remember, this is this. As a function of the lag between my value of the noise, I take the product. And this is the theoretical value of this particular process. And to instantiate your covariance matrix, you will need this autocorrelation, this autocovariance of the process. So here, this is, this is the theoretical value of the autocovariance, which depends on the parameters of my noise. So the bottom line is, in this equation, we know how to define everything. We know how to instantiate the covariance from our autoregressive model. We know the residuals from the model of the astronomical signal. So instead of minimizing the chi-squared, instead of minimizing the distance between the data and the model, I'm going to make the data as probable as possible. I'm going to try to find the parameters which maximize the likelihood, so which make the data the most likely, hence the name likelihood. I will try to find the parameters which make the data most likely. And a simple calculation we can do is that if the noise is fixed, so if we say that this is fixed, and the autoregressive process is not an autoregressive process of order 2, it's just pure noise, these two formulations are equivalent. I thought it would be good to do this simple calculation because it helps manipulate a little bit the notions. So we want to maximize this function. But the covariance is fixed. So this term is just a constant. So if I want to maximize this, it's the same as maximizing just the exponential because it's the exponential times a constant. So you can forget about this. I don't need when I vary my parameters, since phi is fixed, I don't need to vary it. So maximizing the exponential minus some stuff is equivalent to minimizing the stuff here. So I just take this and I minimize this. But the covariance is diagonal. So when I write what it means, this equation, so this is the matrix transpose, this is a vector and I just transpose it. So here you have a line vector, here a big end-to-end matrix, and again a column vector. So it makes a scalar in the end. And when I write what this equation means as a sum, this is what I get. So maximizing this is equivalent to minimizing the chi-squared. So this is exactly what we want. This is a generalization of the fitting process when you don't know what the values of the noise are. And the way we do this is to use a genetic algorithm. So a genetic algorithm will draw a lot of different parameters. It will start from different, so you choose randomly several values for these parameters. And then it will combine the different parameters generated to finally converge to the correct solution. So this is where you start and this is where you end up. This is what you generated here, and this is what you fit, basically, the blue one. We will talk about this on the fourth day. Okay. Model overview. The data is a sum of the signal plus the noise. The signal is the astronomical forcing. It's a sum of periodic term as a function of time. The time depth function is parametrized by n knots. The noise is an autocorrelation and an autoregressive process. And we have all the parameters we need. We characterize at the same time the astronomical signal, the time depth function, and the noise. When we want to fit it, we try to find the parameters that are close, that make the model close to the data in a certain sense. Then we will see tomorrow how we estimate uncertainties, and we will see on day 3 how we estimate this number of knots. Here is a test we did in the paper on simulated data. So the astronomical signal here, it's just the sum of the eccentricity, obliquity, and climatic precession. In our model, the precession frequency is free. The other frequencies are fixed. The data, the fake data, is in the type depth domain, it's equally spaced, and then we will use different time depth relationship to simulate different versions of the data. So these are the time depth, the different time depth relationship that we use. And here the noise in the generation of the fake data is an autoregressive model of order 1. And this is one example. You have the true, in red, you have the true inverse sedimentation rate. In black, you have its estimate plus the error bars. This is in black the fake data. So in black, you have the generated astronomical signal from the simulation plus some noise added on top of it. And in red, this is the signal which is fitted with AstroGeoFit. So this is what we wanted in the beginning. We have a parametric form of the model, and we want to tune the parameters so that our model is close to the data. And this is exactly what's happening here. The model we tuned, the red one, is close to the simulated data. So we wanted to build a model. The data as a function of depth depends on what we want to know. Here we generated fake data. We have a model in red where we put the values of the parameters that were fitted with the maximum likelihood. And so in that case, we know exactly what the simulated signal was. So we know exactly how to separate the astronomical signal from the noise. But I mean, in real life, we will have exactly the same plot, except that we don't have the blue curve. We don't know what the exact astronomical signal is, but we will have a way to fit the data with a model which encompasses all the ingredients we want to have. And that concludes the lecture for today.
Hi, Clara Bolton from Cerej. So forgive me if this is a stupid question. I'm from an oceanography background, not a cyclostratigraphy background. But you say that phase is a free parameter. But how can the model know if there's a constant phase shift relative to the astronomical solution?
It doesn't. I mean, so the thing is, the phase is completely free. So you don't think of it as a phase shift with the where is it? Yes. What I mean is we could have a constraint on the phase if we knew the phase of the astronomical frequency, if we had prior information about what it is. But in the model, we put no prior information on the phase. So it's completely free to choose the phase it wants. So if it happens to be the same as the astronomical signal, okay. If it's different, okay also. It's just not constrained.
There could be a phase shift between one proxy and the signal, and you will output it. It will appear as one of the fitted parameters.
I think one way to reformulate your question would be, if you think of this as a phase shift between the astronomical signal and the response, the thing is you don't know here, the 0 point, the reference of the astronomical signal does not appear anywhere in the model. And yes, it does not appear anywhere in the model, but even if you knew it, you could want to have some sort of delay in the response of the proxy. So the simple practical solution is just to have it as a completely free parameter.
Okay.
If your signal is a noise, if your data is a noise, can AstroGeoFit find a fit to astronomical solutions?
Yes, it can, but you will see on the third day that there is a way to determine if the data is just noise. Because if you have a model and you try to fit it to the data, you will have a fit. No, it's what fits do. So the thing is, you might want to have a test that you're not fitting noise, and this is exactly what we will see on the third day, along with the selection of number of nodes. Because it's kind of the same conceptual framework.
My name is Nathan Hara from Virginia University, Brussels. So what is the real resolution of your calibration? For example, if we use previously we use 400 cycle for astronomical tuning, the real resolution is 405. And within one cycle, the time depth model is interpolated. So what is the real resolution of the fit?
For the what, sorry?
Of the AstroGeoFit.
I'm not sure I understand.
For the calibration, what's the real resolution?
The real what? Sorry.
Resolution.
The real resolution.
Resolution.
The resolution in the resolution in what sense? I don't understand, sorry.
For the
Of the fit?
for the
Yes.
In AstroGeoFit, all the cycles, all the periodicities are fit at the same time. So all of them are real resolutions. It's not like in the visual tuning we use 400 kiloyear or 100 kiloyear to tune. Then the other periodicities, they will be shifted or distorted to some degree. But in AstroGeoFit, all the periodicities are fit at the same time.
Yeah, that's kind of the advantage of AstroGeoFit, is that you fit everything at the same time. So you can see the degeneracy between the different frequencies and the time depth function, for example.
Hi,
Yes.
I'm Thiago from University of São Paulo. You mentioned about the number of knots
Yes.
that control the flexibility of the model.
Exactly, yes.
And I know that the number of knots is a decision from us.
Yes.
But how these knots will be distributed through the series?
So
It's a regular distribution
So
because this can create an effect over your sedimentation rate, right? So,
yes.
But
So
I have the impression we cannot choose by ourselves where exactly to put a knot. This is a software decision.
yes. So the what's implemented right now is you choose only the number of knots, and then they are equispaced on your data. So if your data spans 1 meter and you have 2 knots, they will be spaced by 1 meter. If you have 3 knots, you will have 50 centimeters and 50 centimeters. But now, if you suppose you think that the time depth function has a sort of bump, very localized, then you would want to have knots which are very close to each other. This is not implemented yet, but there's nothing preventing us from doing something like this in a future version of AstroGeoFit.
Yes, in fact, we can set, as it was said, we can set the knots the way we want. It's not a problem of the method. It's just a problem of the implementation. So in future version, we would allow to set up the number of the knots in any way you want.
So the second question I have is related with this maximization stuff you were explaining. This is related with the final result the software delivers. I used the software previously, and I note that we have a median result and a maximum a posteriori result, map, right? Map is the maximization of this.
Yes. So I don't know exactly how it's so, because basically the genetic algorithm is used as a starting point to explore the surroundings and compute uncertainties. This is something we will see tomorrow. And so you can think of the likelihood as like a sort of heat map, or like mountains and valleys, and you want to find the top of the highest mountains. This is what you do with the genetic algorithm. So now you explore these mountains, and maybe in doing so you will find a point which is actually even higher than what you started with. So then I think Arsène knows the details of that, whether the map comes from the initial genetic algorithm exploration. No, it comes from the MCMC. So these are the starting points, and then in your estimation of the uncertainties, you will maybe find something which is higher, and this is the maximum a posteriori.
So the closest, the median is to the map, the better, I believe, because, well, my final result was not so different from the initial conditions.
So the interpretation of the difference between the median and the map is, suppose you have two different solutions that are different in the parameter space. So you have two mountains and a valley. So you have two solutions which are pretty close to the data, but they are different. They don't communicate somehow. So you might have one solution where the model is like this, one solution where the model is like this. And the median might be on top of the data. But one of them is better than the other, and it will be farther from the data. I mean, in that, actually, this particular case won't happen because by definition the map is the closest to the data. But when you have several options, it might happen that the best solution, the best fit, is different from the median fit, where you take into account all the different options.
My question, I'm Kai Xuanji from Peking University. My question is that I understand your model and how to calculate, how to, get the final results. But my question is, our samples from the marine to continental areas. So the environment changed a lot. So the noise ratio to the signal, you cannot test it before we know the data. So it will be large in some the high energy waters or something like that. So is that possible? Use that calculation to, my question is, does the noise ratio influence the final result, and if the noise is really high, so the final result is reliable?
If the noise, I will present on the third day what you can do to see if the noise is dominating or not.
Yeah. Like maybe the noise ratio can be 80%.
Yes. Yeah. So, I mean, the thing is, when you fit your model, you might end up with parameters of the noise. So they are free parameters. So when you adjust your model to the data, you might find that the preferred value of the noise is very high because it's a free parameter. So you let your model decide. So one way to think about this is, this is the data you have. So forget about the red and the blue curve. This is the data you have at first. You don't know who's who. You don't know if the variation is due to noise, if the variation is due to the signal. You just know it's the sum of the two. But in your model, you have the amplitude, the frequencies of the signal, but you also have the amplitude of the noise. So the model might decide to fit your data with a very high value of the noise and possibly a value which is much higher than the parameters of the signal. In which case, you will automatically find that the data is dominated by noise. And the test we will see on the third day will tell you, okay, so the noise is very high, but is my data compatible with just noise? Or do I have a faint but statistically significant astronomical signal? And this is another question. But from the fit itself, just the fit to the data, you will already have an estimate of the amplitude of the noise.
So I don't know how to implement this on my data yet. That's why I'm here. But I did think the record I have is 22 million years long, which is really hard to fit in this in a lifetime. So I was thinking of estimating the reliability, the accuracy of the fit and the accuracy and the reality of the results by using a moving window of AstroGeoFit through the data. And then because the astronomical parameters cannot change at a rate which is large compared to the length of the data sequence, the estimated values must all be consistent if the data
that's a very good test.
If the results are real. Paul Olson, by the way.
Yeah. In fact, you can do that. You can split your data in several pieces also, because of course the quality of the data may not be the same all along. So it's good to start with the best pieces and then make it slide. And also the frequency could change over 22 million years. So right now, we have not implemented yet varying frequency. We plan to do that in next delivery, but not yet now. So the good thing is to have a chunk of solution.
I am Meng from the University of Cambridge. I have a follow-up question following Clara's question. I just wanted to double check for is the phase relation relative to a particular orbital component always constant? And whether we can extract that information after the fit.
So on the duration of the data, the phase is constant. All the phase, amplitude, and yes, the phase, the frequency, and the amplitude, they are constant, and all the variations from a constant frequencies are assumed to be due to the time-depth relationship. But suppose you have data on 10 meters, you could do the analysis every meter, retrieve a phase at every meter, and then see if it evolves or not.
I see. So it is possible to retrieve the phase parameter after the fit.
The phase is one of the parameters.
Yes.
So the fit retrieves the phase. Yes. The fit retrieves the phase, but it will assume that for one component of the astronomical signal, the phase stays the same on the duration for the whole data set.
In the output data file, you will see the phase. Yes. So it will be output.
I mean, all the parameters of the models, all these parameters are retrieved by the fit. It's not like some of them are fixed and some of them are free. It's all of them are free. So the output of the fit are estimates of the noise, of the time-depth transfer function, and of the properties of the astronomical signal. You have everything at the same time. So it's not like the classical way where you fix the astronomical signal, and then you try to estimate the time-depth relationship. Here, everything is moving at the same time.
Steve Hasselbo from University of Exeter. You may cover this later anyway, I think, but I'm wondering what the best approach is if you've got many different data types through the same interval, because phase shifts are probably going to be very different in the different data sets. So how do you combine results from different types of data?
So this is more of a question for Arsène. He's working on this as we speak. Right now. No, but I mean the natural evolution of AstroGeoFit is to try to combine the different proxies. So right now you can apply the fitting process to each proxy independently, and then if there is a phase shift, you will see it, you will estimate it.
Yeah, to complement the answer, yes, we expect to deliver a second edition with the multi-proxy possibility. Because of course, when you have only one solution, one data set, one proxy, you always find a solution and you are happy with it. The problem is there is only one astronomical solution. There was only one value of the eccentricity of the Earth. So you want that if you take several different core or several different proxy, you end up with the same result, which is not obvious at all, because then you really see all the uncertainty in the geological record.
So I guess this is a good way to point out also that when you fit the model, the parameters that you retrieve are the parameters of the model. So the constraints you have on your parameters are just as good as the model. The constraints you have assume that the model is correct. So if the model is incorrect, in the end, the parameters, even if they are very well constrained, if the model was faulty from the start, then even if the parameters have super low error bars, they are still not reliable. So here we tried to make the model as realistic as possible, but it's possible that in future evolutions of AstroGeoFit, we will see that actually we absolutely need to take into account this particular aspect of geological data to include it in the model so that the model is more realistic and the parameters retrieved are more realistic as well.
So Joseph Nar from CEREJ, as Clara. So I'm wondering if you have tried and if you know what will happen if you, as I suspect it may be the case, try to fit data that are following a non-linear response to orbital forcing. And following what you just said, for example, if you can imagine tricks, as in you can find this in some, like forcing some kind of a noise structure that would show patterns that you could attribute to non-linear forcing or this kind of stuff.
So this is a very good question. Here, indeed, the response to the forcing is assumed to be linear. So it's proportional. Maybe there's a phase shift, but basically it's proportional to the... So here, what you could easily do is if the nonlinear response has an effect to make other frequencies appear. No, so for example, if you had a modulation, the product of cosines is a sum of cosines. So instead, you would just add another frequency in the model, and this will be part of the nonlinear response. Now, if it's more complicated than that, maybe it can still be approximated by that. And if it can't efficiently be approximated by that, then we would need to find, here you would have a function of this with its own parameters that you would fit along with the other parameters.
Just to say something, when you look to eccentricity, it is already a nonlinear response, as I was showing. It is nonlinear response. This is why, instead of having the pure frequency, you get difference of frequency. And it's like taking the modulus in the example here.
Yes, this is a good example, yes.
But I think we will, I'm sure you have still plenty of questions, but it's not the only session, and we have still 4 days to go, and we'll have the break, so I think we should go on now. And questions are encouraged, of course, but we need also to go on. Okay, so thanks again, Nathan.